Good afternoon, all. Good afternoon, all. I'm Ms. Tanmaya, lab technician Empri. Due to technical issues, we have started late, quite late. Sorry. Okay. I welcome you all to the third webinar on tropospheric ozone and hydrofluorocarbons as climate pollutants under the webinar series, Role of Short-Lived Climate Pollutants in Climate Change Mitigation. I welcome the speaker for the day, Professor Gufran Ullah Beg, Founder Project Director, SAPAR, India. Sir Ashutosh Mukherjee, Chair Professor, National Institute of Advanced Studies, NIAS, IASC, and Dr. Tejaswini M.E., Empri Fellow, Climate Change, Department for Climate Change, Empri. I would like to extend a warm welcome to our Director General, Dr. Jagmohan Sharma. I also welcome all the participants and Empri staff to the webinar. Moving forward, a brief introduction about the speaker. Professor Gufran Ullah Beg was the Program Director of System of Air Quality Forecasting and Research, SAPAR, a network of air quality and weather monitoring stations which assist in the forecast of air quality and in maintaining an emission inventory. An elected fellow of the Indian Academy of Science, he received the Norbert Gabor-Moe International Award of the World Meteorological Organization in 2005. The first Indian to receive the honor, the Council of Scientific and Industrial Research, the apex agency of the Government of India for Scientific Research, awarded him the Shanti Swarup Bhatnagar Prize for Science and Technology, one of the highest Indian science award for his contribution to Earth, atmosphere, ocean, and planetary science in 2006. Professor Gufran Ullah Beg will be taking on the topic tropospheric ozone, a polluter and climate forcing agent. Thank you, sir, for accepting our invitation and gracing this event with your valuable presence. If you have any questions during this webinar, please type them into the chat window. We'll address them during the question and answer. Over to you, sir.
Yeah. Can you disable the screen sharing? Can you disable the screen sharing? Because I'm not able to share the screen.
Sir, are you not able to share the screen?
Yeah, host disabled participant screen sharing. Yeah, host disabled participant screen sharing. It is coming like that.
Okay. Just give me a second, sir. Please try again, sir.
Okay. Can you see the screen? Hello? Are you able to see the screen of mine?
Yes, sir.
Okay, so I can start the talk.
Yes, please.
Okay, so good afternoon to all. As the title suggests, my topic of today's talk is tropospheric ozone and climate change. And this ozone, if you talk about ozone, that is has a dual role to play in the atmosphere. First is that it is a deadly pollutant which harms your health, as well as it is a greenhouse gas. Now, I will start from the fundamental facts that tropospheric ozone, which is the topic of my talk, it is a part of the tropospheric chemistry. And tropospheric chemistry is dominated by one of these, one of the gas, which is ozone. And when you talk about tropospheric chemistry, it impacts the climate change because control the radiatively active species, including aerosols, ozone, methane, hydrofluorocarbons, carbon dioxide, nitrous oxide, and all those things. Then it consists of a regional air pollution, surface ozone, visibility, air toxicity, acid rain, and all those things. Then from the stratosphere, which is the oxidation of the HFC gases, there is an intrusion from top to the troposphere, and that is where the stratosphere is coming into the picture. And at last but not least, that ecosystem, where nutrient transport and deposition of a nitrogen, trace metals, and all those are also found in that. So the larger picture is that tropospheric chemistry, where tropospheric ozone is a part of it, it plays a very important role in that one. Now I am coming to the fundamental facts here. When we talk about climate change and ozone, then many people have a belief that carbon dioxide is the only one which provides us with the climate change. We are not responsible for other gases and all. But there is a terminology, what we call is a short-lived climate forcing parameters, in which there are many of them are the parameters which are good for, which falls under the category air quality. Now here you will see that aerosols, basically the bigger air particles, when the solar radiation comes, it reflects back. So in a sense, it is countering the global warming, and it is that is why it is called as a solar dimming. And all greenhouse gases, as you all know, gives rise to warming, which you can see the red, this maroon box, where all greenhouse gases together is providing this much warming, and this much is cooling offset by the aerosol. But this aerosol as such is not a good to increase, but when it is increasing, you may see that it is good for global climate change, which is offsetting some of the global warming. But when you come to its impact, indirect impact, that's not a good thing to be increasing. So what the point from this slide you want to draw is that air quality regulated aerosols are the largest factor offsetting the greenhouse gas forcing. Now, another comparison you will see that what we call is a climate forcing parameters, which is in the right hand side, and then the left hand side, it is the air quality. So normally the aerosols, direct or indirect, that is all we call is a air quality. But in air quality, when you will see in the right hand side, tropospheric ozone is one of those greenhouse gases which give rise to warming because of the structure of black carbon that also absorbs the greenhouse solar radiation and give rise to global warming. So the point is that air quality parameters not only provides you the global cooling in terms of a aerosol reflectivity, but also contribute to the climate forcing. So what you can find out that CO2, methane, nitrous oxide and all, they are very difficult, or we are becoming very, very difficult to, because of the dependent of the energy to fade it out, and then energy balance has to be maintained unless you come out with a very, very robust technology replacing fossil fuels and other things. Regulation of the certain short-lived forces would provide short-term climate benefit maybe in next 5 to 20 years. So you are not only dealing with the or curbing the climate change, but also it will provide the relief from the health point of view. So co-benefiting for health and climate if you can control short-lived climate forcing gases. So air quality and climate policy and their impact need to be examined together and based on sound scientific knowledge. That is what the conclusion which comes out from here. So as I already told that air quality and climate, methane is also one of those. Then this tropospheric ozone, black carbon. So you see that how much air quality is taking role in climate change debate. Now, when we talk about atmospheric chemistry, we talk about a continuity equation. Which, why I am telling this is a little technical, but why I want to tell you about this is that in a continuity equation, the rate of change of any species, production minus loss, and the transport loss term, delta into F, where the metallurgy and dynamics comes in picture. P is a production, means that is nothing but an emission, and L is a deposition, means there is a loss. When we deal with the air quality or any kind of a chemical compounds like ozone, global issue, when we talk about intercontinental transport, regional issue is a synoptic weather related transport, and local issue is always the emission. So these are the three parameters which controls any species, whether it is a tropospheric ozone or a stratospheric ozone or any other parameters on that kind of thing. So the emission becomes one of the most important factor in the research fraternity which need to be dealt with. And as I told that emissions, whether it is globally, regionally or locally, finally in an intercontinental transport or synoptic weather related transport, but it is something which is emerging in any part of the world from the emissions, and then that is also getting transported. So emission continue to remain as a one of the fundamental parameter of that. Now coming to the major topic, which is basically ozone from a very fundamental point of view, is a trioxygen, is a triatomic molecule consists of 3 oxygen atoms. It is an allotropy of oxygen that is much less stable than the oxygen which you talk about. So oxygen has a much longer lifetime as compared to ozone. 2 molecules versus 3 molecules. Ozone is a gas that occurs both in the Earth's upper atmosphere and at the ground level. The last sentence, when you read, there are many youngsters, even of the senior people, who get confused with the good ozone as bad ozone, because for last 3-4 decades, we have been hearing that there is an ozone hole. Ozone is depleting and we need to fill up the hole, means increase in ozone. So if increase in ozone is required for us to survive, then why we are telling that ozone increase is not good? And that is where it matters that ozone can be good or bad for people's health and for the environment, depending on its location in the atmosphere. And that is where is the key for that. So now this particular diagram will show, this is very simple diagram. When you see that Earth's surface, which is a 0 kilometer, when Earth is written, here we produce the emissions of ground level ozone, greenhouse gases, major compound of smoke and everything, aerosol spray, fossil fuel emissions, fine. So there is a lower atmosphere where basically it's about 15 kilometer for the tropics. It varies from 8 kilometer to 18 kilometer. In our region, let's say in Bangalore, it is about 15 kilometer. So up to 15 kilometer, whatever is the ozone which is there, that is very deadly. It is a pollutant, it is a greenhouse effect, all bad effects. So that is what it is called bad ozone. So 10% of ozone in the troposphere, it is coming from the downward intrusion from the stratosphere. But most of the ozone resides in the stratosphere. 90% of the ozone is in the stratosphere. And there you will see that it is produced by the chemical reactions. It is not because of any emissions or anything of that kind. When sun rays are there, good ozone in the stratosphere because it protects us from ultraviolet radiation, because if ozone is more, the dangerous radiations would be absorbed there and then and there itself, and it will not arrive to the surface. So we will not have any problems in terms of a UV radiation, which is very harmful for skin cancers and many other things. Whereas if that ozone is declining, then more and more UV radiations will escape near us, and then we will start having a skin related all kind of diseases which can extend up to the cancer. In early, let's say that about 1980 or so, that time there was in a World Health Meteorological Organization and United Nations Environmental Protection, they came up with a very categorical understanding and a statement that scientific evidence and new analysis demonstrate that control of black carbon and tropospheric ozone through rapid implementation of proven emission reduction measures would have immediate and multiple benefit for human well-being and climate. So there was an integrated assessment of black carbon and tropospheric ozone was prepared. That particular, you may find particular, I think this report in a internet, which may be freely available. But that was first kind of in early 80s, first kind of a solid statement from two world bodies, which are the topmost bodies in environmental science, where they have clearly written that these are the two things which then people started talking and people started making. Otherwise, we were thinking that troposphere only 10% of the total ozone and 90% in the stratosphere. How does it matters and all? But then, and then finally it has been found that this ozone is rapidly increasing in the atmosphere. Well, this diagram is not to confuse you, but to make you aware that how atmospheric concentration of ozone is important not only from climate point of view, but for atmospheric concentration of methane, VOC, CO from where it has been produced. How come this methane, VOC, CO, NOx, they come? They come from pollutant emission, which is in the bottom, fossil fuel, biomass burning industry, emission related land use, land cover change and all. Then same these emissions, the green box where nitrogen cycle emission, environmental concentration, and then again it goes back to the climate. Then these nitrogen cycles in the upper atmosphere, it produces ozone. So this is particularly Earth system, whether it is a tropospheric ozone or a stratospheric ozone. This is what it is making a full circle. So finally, with this discussion, what the conclusion we came out? That is what I had given the name with ozone climate, changes in tropospheric temperature and water vapor resulting from climate change, because you must be all hearing that global warming and all those. So that is what changes in tropospheric temperature and water vapor resulting from the climate change will not dramatically modify tropospheric ozone. So because of the climate change, tropospheric ozone is not going to make much of a problem, but changes in emission generated by climate change due to human activities will have a profound impact. So finally what we are boiling down to it, whether it is a climate change or whether it is tropospheric ozone, it is a sources of these pollutants or emissions of these which is going to make a profound changes. And then when that is happening, then this is leading to tropospheric ozone elevation. If tropospheric ozone is increasing and it is also a greenhouse effect, it will give the climate, it will warm the atmosphere, make a climate change, and then the cycle continues. So the point is that it is an unending cycle, feedback from one and giving rise to. So the ozone becomes one of the most tricky and most critical parameters for the climate change to happen. And that is why the scientists, in spite of the fact that concentration is so low, even then they feel that doing little will yield more benefits with that. And that is what started coming. Well, this is all I am talking about the chemistry, that how this ozone is produced, whether it is in the near the surface or whether troposphere, pollutant packed together in direct sunlight. So it is like a baking. Now you make a baking cake from in the microwave oven or something. So similar way, if you bake in the sunlight is like a microwave oven, where you are baking like a baking soda, NOx, VOCs, which is going to give you the final cake, which is like a ozone. But this is a very dangerous cake. So ground level ozone and tropospheric ozone is being formed like that. Now sources, you should know that ozone is a secondary pollutant which is produced in the troposphere by the chemical reactions of certain chemical species. Those chemical species are the primary pollutants which is entering in the atmosphere through the different sources which we produce. So NOx is, so they are called precursors like NOx, VOC, carbon monoxides. So here you will see that this is over the Indian region. These are the things which is made. For example, VOCs, where 50% of the emissions are coming from the industrial sources, 45% from the transport, whereas in NOx, there's about 60 to 70% is from the transport sector, utilities, industries, and all other sources. So basically what you are trying to put it here is that as far as gaseous pollutants are concerned, mainly the industrial activity, biomass activities, and transport related activity, they are the ones which are creating a problem. But the point here is that why should we worry about that? And that is something which is very, very, very dangerous and from terrifying. That since ozone is a strong oxidant, tropospheric ozone is harmful to human and ecosystem. And that is a depiction of one of the pictures that from the fossil fuel, from the transport particle, the pollutions are coming, it is getting, and then since it is a gas, if particulates are there, they get stuck in your natural system. But since it is a gas, it gets mixed with your oxygen, which you inhale, and it can reach up to the lungs. And once it can reach to the lungs, then it can start damaging you like anything. So it worsens bronchitis, emphysema, asthma. Bad ozone is also can reduce lung function and inflame in the lining of the lungs. Ground level ozone lead to damage in agriculture also and field also. So that is something. The point is what I'm trying to draw from here is that it is really bad. Now whole lots of area of research is going on where as compared to other pollutants which you call about PM2.5, PM10 and all, ozone as such is a very harmful to the plants and their leaves, because particulate matter and other, they are damaging plants and others externally. But this particular gas damage them internally, and through internally it is damaging your external organs. So that is why when ozone is incorporated in the plant, it produces reactive oxygen species. So in metallurgical or agrochemical ozone fraternity, people talk about ROS, which is reactive oxygen species, induce synthesis of the several plants hormones, and then accumulation of this particular gas causes either lesion or chronic leaf damage, as you can see in this one. This kind of a leaves you must have seen in many places when you must have visited or all. Well, before I come to the radiative forcing, I would like to just show, for the sake of curiosity of many youngsters who must be listening the talk, that these are the who is who in ozone, whether it is a stratosphere or it is a troposphere, who has made us enlighten about this wonderful science of ozone. And they are the one who are the brain behind it, mentors in a different time scale from 1936 onwards. Number of them have got the Nobel Prize. Many of them is fellows of Royal Society of London, and many. So all of them have written. So, but in all this lot, there was a second ozone conference, which is still continue to happen every 2 years. This conference, the second one has happened in Oxford in 1936. What point I would like to make here is that out of this total lot, there is one scientist from India which has participated, which I have circled with the yellow elliptical circle, which is Professor S.K. Mitra, whose books also you can see the aeronomy of the middle atmosphere, or stratospheric ozone, or science of the science of chemistry of the atmosphere. Number of books are there, but one book or other is highly regarded. So in library or somewhere you will see. So he's a gentleman who has who is like a father of chemistry or this thing in India, and his student of him was Professor A.P. Mitra, who was Director General of CSIR, and I have been fortunate enough to be a student of Dr. A.P. Mitra. So this is the reason that I keep proud in telling this, that in a sense that he is my grand supervisor. Well, now coming to the point is that major type of radiative forcing in the atmosphere, which we are more concerned about in this time era of climate change, which is greenhouse gases, aerosol, surface albedo, contrails, solar variability, volcanic activity. All those are the one which somewhere or other disturbed our radiative or a radiative system. In the sense, what a radiative system is in a very simple way. What way we get heating and cooling in different seasons or different places at a particular point of time. Whether it is a heating or whether it is a cooling, everything falls under radiative balance, radiative impact. Now, this is little fundamental thing where you can see that what is radiative forcing. So, a starting point of consideration is basic structure of the temperature versus height, which is given here. From the surface, below 15 kilometer, it is our troposphere. Above, it is a stratosphere. So you'll see that radiative dynamical balance and then radiative balance up. So the point is that because of the ozone, as we go away from the surface, temperature declined from on an average 15 degrees Celsius near the surface. It goes up to about minus 70, 80 degrees Celsius at the tropopause, where this line, black line, is cutting the thick blue curve. And then suddenly after that, because ozone is present in the atmosphere, in the stratosphere, it starts absorbing these gases, the radiation, and temperature in the stratosphere at about 25 or 30 kilometers within a span of 10 kilometers, it goes up to about 20-25 degrees Celsius, much more than what we have near the ground. So you see the power of this particular ozone gas. Because of that only this temperature is happening. And after that, the moment impact of this stratospheric ozone goes off, it is again starts cooling because you are going away from the source of heat from that. Now, importance in terms of a radiative forcing of this tropospheric ozone. This is very important for you to know that tropospheric ozone has a radiative forcing which is almost 1,000 times higher than CO2. List of others also written down, but tropospheric ozone is 1,000 times more dangerous in terms of providing a global warming as compared to CO2, which we talk about normally these days. But then obvious questions must be coming in your mind that if it is so, why ozone is not considered as a major threat and everybody talks about CO2? Answer you need to think, but anyway, I will provide the answer is that, see, the quantity of the CO2 is much higher as compared to the quantity of ozone in the troposphere. And that is the reason that flux is very less. So even if it is 1,000 times more dangerous, concentration amount is so less that it is not matching with CO2. But the worry is that with this, if the amount goes rapidly high, then it will leave CO2 behind. And that is what is the worry. So if you see, compared to CO2, methane is 25, GWP is nothing but a global warming potential. So compared to CO2, how much time more it has a ability to warm the Earth atmosphere. That is what the meaning. And HFCs, you will see, it is something like 14 to 15,000 times higher as compared to CO2. So you just see now that what kind of a impact it will leave is on the Earth. Well, there are a number of time when people have shown, this is one of our paper, some about 10 years back, where we try to see that we try to run the model, which is a chemistry model, which says that in 1900 AD, the ozone in one of the best month, which is a July month, which is basically over the Indian region, it is more of a rainy season, where the ozone at present, if it is of this order, which is purely in a purple 10 to 20 ppb, then by the end of this century, the ozone is likely to go to about 50 to 90 between this thing, because as you will see in Indo-Gangetic plain and upper part of the atmosphere, you will see that the values are going as high as 80, 90, whereas even if the cleanest area, if you'll see in the southern peninsula, so in that also it is going at least more than 40 to 50. So the point is, from 20, you are going into this, which is almost double or triple of that present concentration by the end of this century. And this is something which is really alarming. If this happens and we do not control it, our radiative forcing, we will continue working on a alternate solution for CO2 by electrical vehicles and many other things. But suddenly another enemy will come in terms of a tropospheric ozone, and we start then. So better start thinking now rather than start thinking in a later case. This was another paper where, using the model as well as using the observational data from the satellite, in 2009 in a paper in GRL, we have found out that already from 1979 to 2005, means in 26 years, ozone has increased by about 6 to 10% in over the Indian region. You will see this is what is the Indian region, where you will see most of these are red or yellow, and this is what red. So it's about 4 to 8% has already increased, and now the changes are even much more rapid as our developmental activities are increasing. Well, these are some of those total ozone related things that if you talk about total ozone, then until recently, the stratospheric ozone was increasing and tropospheric ozone was increasing. Now, because of the Montreal Protocol, the ozone hole, what we used to call, or when where the ozone was declining much faster, has ceased, because that is one of the most successful scientific treaty where we are able to replace all the CFCs by HFCs, and because of that, because of the replacement of HCFCs, we are in control of ozone, and ozone started at least no more increasing. It is on the path of recovery. Now, this particular slide is showing that radiative forcing doesn't scale linearly with concentration changes of ozone. Net ozone change and radiative forcing have different signs. For example, when ozone is in the stratosphere, which is from 15 to 50 kilometer, ozone change since pre-industrial era is about declined by 20. This is something which has happened during the last from 1850 until recently. But tropospheric ozone has increased by about 7 to 8% at this stage of time. And because of that, there is a positive radiative forcing, which is in maroon color, which has gone up to 20 to 25 watts per meter. And total, when you combine all together, it is all the time that because as far as radiative forcing is concerned, the problem is mainly the positive side, which is more that ozone is increasing in general in the troposphere and making the radiative forcing much higher as compared to that. Now, there are many things, there are many complications. I am not going into detail of that, because stratosphere and within the stratosphere itself, it is not only that ozone increase is leading to warming at that area, but because ozone, some of those gases which are very close to the tropopause, because of the lower intrusion, there would be kind of a warming it provides in the troposphere also. So that is what we call is a long wave and short wave related heating that results from stratospheric ozone depletion, partially offset its long time cooling. So now, point coming out with this in general is that in the era of climate change, now I have some 3-4 more slides and winding it up. Now I am focusing on what we should do, what the frontier research all over the world is going and taking a path. And if we adopt that particular thing, which I am going to tell in next 2-3 slides, we are in the frontier of research in this area of SLCPs. So these are very important for you to listen, and for the future development and future work in this direction, which is going to be the talk of the town in the coming few decades. Identification of most critical short-lived climate parameters and the emission inventory development in South and Southeast Asia, with a priority focusing on hydrofluorocarbons, methane, and ozone. Planning for long-term monitoring, since monitoring of SLCPs is poorly done in this region with a focus on India to work towards development of alternative climate and ozone-friendly technology in search of alternative HFCs with a low global warming potential to avoid potentially serious problem. Because in our country, cooling demand with the climate change is going to increase significantly. So we are going to use more and more coolant, which consists of high global warming related but less ozone depleting HCFCs, which is not good for us. Whereas Western countries already got the cooling demand as much as they want already. So the point is that we are the one who are going to get a maximum brunt of that if we do not follow that, because we are in the developing stage. We are developing. Our economy is booming. So to provide short-term basic training course tailored for different grounds in this area to enrich communication and outreach activity. What I inferred from my talk and what is there in the future to come, tropospheric ozone is increasing rapidly. Strategic ozone was decreasing, but now on the path of recovery and almost stopped to decline. Ozone radiative forcing is positive, reflecting a greater contribution from tropospheric changes as greenhouse gas. Positive means it is warming, so it is contributing to climate change. Stratospheric ozone depletion leads to tropospheric cooling indirectly, that was offsetting its effect. So when tropospheric ozone was increasing, stratosphere was declining. In terms of a radiative forcing, that was a good thing which was happening. It was offsetting. But the point was that stratospheric depletion was even deadly because it is directly impacting our health and life. So it has to recover. So stratospheric ozone, when it is recovering, radiative forcing is the sum of. So, but now that stratospheric ozone is recovering, impact of greenhouse effect of tropospheric ozone will be faster. That is the current worry. And in view of this, future research pathway should be that accelerating research and advocacy on SLCPs today will be critical for our common future and key research initiative. SLCP's potential to warm the atmosphere is many times greater than other greenhouse gases. Basically, at this stage of time, about 45% of the global warming is happening other than CO2. And SLCPs are powerful climate forcers, but influence is quickly reduced due to their shorter lifetime. Some SLCPs are also dangerously air pollutant that have a harmful effect for people, ecosystem, and agriculture productivity. Hence, if you are controlling that, you are controlling not only the climate change, but controlling your health also and benefit for the health. Methane, tropospheric ozone, HFCs, and black carbons are responsible for 45% of the global warming, thus most important after carbon dioxide, as I already mentioned. But we do not have any reliable fine emission entry except some crude gross estimate of methane and CO2, and hence require a huge amount of work, which is time of the need of the hour. Recognizing that what cannot be measured cannot be managed, measuring and estimating emission from source are essential element in the success of net zero, which Government of India is promised by 2017. And NIA's expertise the methodology, hence we together can make a significant contribution benefiting future generation and policy makers in government. And with this, I think I stop my talk. Thank you. So I have completed my talk.
Thank you, sir, for giving a brief insight on tropospheric ozone. We are all grateful for the time and effort you took to share your thoughts and information about tropospheric ozone. We have another speaker for the day. Do you have any questions?
Yeah, so if somebody
please
is
unmute yourself and ask the questions.
So thank you for that very insightful talk on tropospheric ozone impact on the planet. You've given a very brief for answering the picture today. So I have one question about estimating tropospheric ozone.
Voice is very slow. I can't hear it.
Is it better now, sir?
Little better.
Okay. So I was wondering about quantifying tropospheric ozone concentrations. And you said, I mean, we all know it is a secondary pollutant. So, like direct emission estimation cannot be done. But could you please give us some insight on how else quantification of tropospheric ozone could be done?
Well, as I could hear from you, is that 45% contribution in global warming, not only troposphere, but other than CO2, where this tropospheric ozone, CFCs, black carbon, and methane all together is responsible for about 45% of the global warming, which is second highest to carbon dioxide.
No, sir. Can you hear me now?
Yeah, your voice is echoing.
Sir, is my audio better now?
Yes, now better.
Okay, sorry about that echo, sir. So, like you were mentioning that tropospheric ozone is a secondary pollutant, right? So there is no direct source of emission or anything. But could you please provide some insight on quantification of the tropospheric ozone, sir? Since emission based quantification cannot be done. So how else do we quantify tropospheric ozone?
Means in terms of emissions or something you are talking about?
Yes, sir.
Yeah, see, tropospheric ozone is produced certainly with the tropospheric ozone by the chemical reaction. But then tropospheric ozone production of that is responsible due to the emissions from their precursors. And these precursors, major precursors are three precursors. One is oxides of nitrogen, what we call is a NOx. Another one is a volatile organic compound. And third one is a carbon monoxide. Where these are the one which is directly emitting their emissions from the surface, and they also have a different contributions. For example, so these are the only one non-methane hydrocarbons, methane, non-methane hydrocarbons, what we call is a volatile organic compound, CO and NOx. Now, for example, I will say that VOC and NOx, CO is contributing, but relatively less. So let us consider these two. And there I have shown that quantification of them are VOCs are mainly coming from the industries where the dominating source is industry, and second is a transport. Whereas as far as NOx is concerned, the dominating source is a transport sector where about 60 to 70% contribution. Then comes the biofuel emission, and then comes the industries. So basically the three sectors, transport sector, biofuel means residential sector, and industrial sector. Now as far as industrial sector is concerned, that is all being taken care in a sense that there is a much more stronger control is there because they are the point sources. So our major worries remains in the two sectors. One is the transport sector, which in a sense, because they are very important from a particulate pollutant points of view also. So we are taking a good steps in that, in converting into the electrical vehicles or anything. But then the most important thing which is left out, and due to which the ozone pollution is much more likely to be much more dangerous and dominant in a rural areas as compared to urban areas, because people are using the biofuel there, wood, kerosene and all. So these are the two sectors which I feel that which is indirect contributor to ozone.
So like an estimation of emission, could it be done based on these two emissions, sir?
Estimation of these two emission inventory has to be developed for these three secondary pollutants, but then the concentration or the estimation of their reduction can only be done using the chemistry transport model, because finally emissions give rise to the concentration, and that is what ozone concentration we are we are concerned about it. But there is nothing like emissions of ozone, because they are and moreover the emissions of NOx and VOCs which I talked about is not directly proportional to the concentration, because it's a very non-linear relationship. If you say that let us say that NOx is reduced by 50% and then VOCs are reduced by 50%, then ozone will be reduced by 50%. No, it may not be true. It may be 70%, it may be 30%. So it is a combination, because I didn't talk about even more. For example, you must have seen that in Delhi, ozone is very low, which is very good, but it is a blessing in disguise. Because what happens that NOx emissions are so high there that are above certain level of NOx, it start depleting ozone. So why I am telling blessing in disguise, that it start depleting ozone. So ozone is anyway, it is reduced in the city area, but NOx goes extremely high, and it has its own health impacts.
Okay. Okay, sir. Thank you very much.
Yeah.
Any other questions from the audience?
So, Professor, I have a question to you.
Yeah, please.
Then essentially, there are models wherein the emission of, say, VOC or NOx is taken as input.
Right.
And then the model is able to generate some kind of a scenario, especially of the ozone that gets produced. Is that right to say?
Exactly. And this is what we are expertising in that. All this forecasting model. So forecasting model of atmospheric chemistry is something which is much more advanced version of what we are talking about, because we will be doing the offline calculations. So
thank you.
You are absolutely right, whatever you said.
Thank you, Professor.
Thank you, sir, for giving a brief insight on tropospheric ozone. We have another speaker for the day, Dr. Tejaswini M.E., Empri Fellow Climate Change, Department for Climate Change, Empri, who will be talking on the topic hydrofluorocarbons and climate change. Dr. Tejaswini completed Bachelor of Engineering in Biotechnology from PES University, MTech from Manipal Academy of Higher Education, and PhD in Environmental Technology from Tampere University, Finland, under the Marie Curie European Joint Doctoral Program. Previously, she worked as a scientist and coordinated the NGT monitoring cell at KSPCB for Chief Secretary, Government of Karnataka. Currently working as an Empri Fellow Climate Change, she has 5+ years experience in field related to environment and climate change, and has several peer-reviewed publications and national, international conferences presentations. Over to you, ma'am.
Before Dr. Tejaswini starts, Professor, are you going to stay back for a talk, or?
I will be there for some time, because I have a meeting another within 5 minutes.
Right. So I just wish to convey my regards to you and express my thanks to you for being part of this workshop as an expert person, actually. As you understand that we are in the process of developing SLCP inventories for the state. So thank you very much, and please keep supporting this project, which is steered by Dr. Tejaswini. Thanks for your presence.
Always a pleasure to be interacting with you and your group. Wonderful.
Thank you.
Thank you, sir.
afternoon, everyone. So I will be giving a brief overview about hydrofluorocarbons and how they are going to impact climate change. What are hydrofluorocarbons? They are a group of synthetic gases primarily used in refrigeration, cooling, and air conditioning purpose, and also till some extent for insulating foams and aerosol propellants. So hydrofluorocarbons are these synthetic gases, which mainly comprises of 2 to 5 molecules of carbon attached with fluorine and hydrogen. So these were invented as a replacement of chlorofluorocarbons. I am sure everybody in the room is very well aware of the chlorofluorocarbons, which was a very big concern as ozone depleting molecules in the 1990s. So to avoid their emission or usage, hydrofluorocarbons were introduced. So a hydrofluorocarbon emission does not occur like, intentionally, unlike, for instance, if you see NOx or SOx emissions from transportation sector, the minute you're burning fossil fuel, there is some emission, right? NOx or SOx that you can directly relate to the fuel burnt. Unlike that, HFC emission mainly occurs because of leakage or during maintenance or disposal of those air conditioners, etc., at the end of their lifetime. So by telling this, I want to imply the point that recovery is still an option there, right? And the main concern with hydrofluorocarbon as a climate pollutant results from these factors, which are quoted to the end of the slide. Despite having an average life of 15 to 29 years in the atmosphere, please compare this to CO2, which has 100 years plus. So anybody can easily see that this is 3 to 6 times much lesser. Despite that fact, the contribution of HFCs to the global warming is up to 3,790 times higher than that of CO2. This is up to, that is, this is the global warming potential of the most potent HFCs. So it ranges from 1,500 to that number. So one molecule of HFC is equivalent to at least 25,000 molecules of CO2 in terms of global warming potential. That is how we can correlate. And another very concerning issue is the fact that HFC usage is seeing an annual growth of 10 to 15%. And this is very much a fact in a country like India, which is like, developing into a economically stable country, and where global warming has a very pronounced effect, and the heating is happening, and more middle class group of earning income is increasing. Thereby, more people can afford these conditionings, and that way contribute to the higher leakage. So here is a list of different types of refrigerants and foam blowing agents that are used in various sectors. So here I just want to show the sectors mainly, which are where hydrocarbons are used, like mobile air conditioner. By that, I mean air conditioners in your cars and buses and other vehicles, room air conditioners, and packaged direct expansion. So, and refrigerators and chillers and industrial refrigeration, etc., cold chains, and foam blowing agents, foam that is used for cushions and insulating purpose, etc. So, please take a good look at this graph. Like any other climate or air pollutant whose concentration is increasing steeply in the last few decades, right? But here the starting point of near zero PPT in terms of mole fraction of one of the HFCs is 1995. So this is a very recent concern, and over such a short duration, the increase in the atmospheric concentration of such HFCs has gone rapidly up. So how do HFCs impact? The refrigeration and air conditioning are responsible for emissions of up to 4.8 gigatons of carbon dioxide equivalents. which will rise to about 12 gigatons by 2030 under a business as usual scenario by one study conducted by Kumar et al. In 2018. It was in 2018, so that prediction was 12 years later, but I am sure if we measure the equivalence, it's already reaching the target. So the emissions, 1/3 of it come from the use of direct refrigerants, right? When these HFCs are used, their leakage is causing global warming. With that, about 2/3 of the emissions in terms of CO2 equivalents come from energy consumption. So I'm sure you all know to run the AC, you need electricity. So for that, again, there is carbon dioxide emission. In case of transportation, right? The minute you turn on your AC in your car, your mileage goes down. I'm sure our fathers start complaining, put off the AC, we are wasting the fuel, right? So there is a good reason behind that. So up to 15 to 20% of your fuel is used up by air conditioning when you put it on an average speed. So HFC especially has an avalanche effect, right? So the more global warming occurs, the more people want to depend on air conditioning. That way more HFCs are released to the atmosphere. And this has caused or leading to this phenomenon of global boiling. I'm not sure if everybody came across this term. Recently, the secretary to the UN used this term global boiling because July was the hottest month ever recorded across the globe, right? So people, I mean, it's not scientifically based yet, but people are starting to think we've passed the era of global warming and now we are entering the era of global boiling, right? And HFC has a very, very huge potential to, like, you know, accelerate this cause. So Kigali Amendment of the Montreal Protocol, which was signed in the capital of Rwanda in 2016, targets HFC emission. I'm sure everybody knows what Montreal Protocol is. It was signed to reduce, signed to target ozone depletion, right? To reduce the CFCs, thereby protecting the ozone and reduce the ozone holes. So the initial aim of the Montreal Protocol, that is saving the ozone, stratospheric ozone, is now fulfilled. And somehow, as a result of it, HFC emissions to phase out CFCs did start in the early 2000s. But again, the Kigali Amendment in 2016 targeted HFC emissions in particular. So it is an international agreement which was aimed at gradual reduction in consumption and production of HFCs, right? Please mind the production as well. We cannot target only consumption when the production is occurring. So industries or a country is also somehow pushed to find alternatives for HFCs, because the dependence on air conditioning as such cannot be avoided. If we are sitting in a room in an office, you cannot just say not turn on the AC, but we need some technological innovations wherein the dependence on HFC is reduced. So consumption as well as production needs to be reduced. So the commitment as per this agreement is by 2011, compared to the 2011 and 13 emissions, the first group of country, which is like old industrial countries, you can mainly see the westernized countries, they have signed to reduce HFC emissions by 45% by 2024, next year, and by 85% by 2036. The second group, which includes countries like China and Brazil, they have signed to reduce 80% of HFC emission by 2045. And 2047 is the target for the rest of the countries to reduce emission by 80%. And this includes countries like India and many other Middle East countries. So by mentioning Middle East, I'd like to bring to notice that they are hugely dependent on air conditioning, right? Because of the weather conditions that are prevailing there. So here the global map, there is a representation of how many countries have ratified this Kigali Amendment as on June 23. And as you can see, majority of the countries have ratified it, except a few in the North African and Middle East countries. But overall, there's a good acceptance for this amendment to phase out HFC. And the good news is, unlike CO2 emissions, where we do not foresee a scenario wherein CO2 emissions could be controlled, HFC control is possible because there are several other alternatives. So with some effort from policies and industries, there are surely many alternatives for HFCs. So here is a study which shows CO2 equivalent emissions of HFCs projected until 2050. As a baseline scenario, with whatever the trend was in 2015, based on that, if the HFC emissions continue to happen, you can see that amount of CO2 equivalents that are going to be emitted, right? But Kigali amendment tries to bring down that emission, and the current policies that are like globally averaged policies is somewhere half through it. So that definitely means we are working in the right direction globally, but more effort needs to be done. So a successful HFC phase down with the implementation and ratification of Kigali Amendment is expected to keep the global warming, avoid the global warming by up to 0.4 degrees Celsius by the end of this century, while continuing to protect the ozone layer. So with the target of 2 degree, 0.4 degree, you can see that is a very big contribution, right? So a lot of seriousness is going into this amendment. So that was a global perspective, what is happening in India. So one of the studies by Kumar et al. 2018, they suggest that cooling energy demand of India is predicted to double by 2027 as compared to 2017, right? Because of increase in temperatures as well as the earning middle class, increase in the number of middle class population. And 57% of all Indian energy demands for cooling come from buildings. By cooling demand, I'm also including fans and these conventional coolers, all of that. In any case, 57% of the energy demands with respect to buildings comes from cooling. By that, I mean to say, if you go back to your electricity bill in your home, 57% of that will be because of fan or air conditioning that you're using on an average. Compared to 2017, around 25 gigawatt of new coal capacity can be avoided by energy efficiency cooling, right? By in 1 decade, by 2027. That is, if we implement efficient cooling and energy translation properly, up to 100 metric tons of carbon dioxide equivalent emissions could be avoided. So that is the potential that the cooling sector holds. And the cooling sector is mainly fueled by HFCs. So as such, there is no HFC study. So we're taking this cooling demand as a proxy activity for HFC emissions. So as per this Kigali agreement, India will need to freeze its HFC consumption in 2028 and will have to reduce it to 15% of the baseline in comparison to 2010 by 2050. That means 28 could be this peak of the bell curve wherein the emissions of HFC can happen. After that, we will have to somehow make amendments, policies, and encourage industries to come up with alternatives so the emissions go down. So 2028 is the freeze year for India, as suggested by the agreement. So here is a chart of the energy consumption, right? Annual carbon emissions, which is a proxy for energy consumption. In 2017, compared to 2027, business as usual and improved scenario, wherein you can see the majority of the emissions come from space cooling and mobile air conditioning. And industrial process cooling is, of course, contributed to a certain extent, but you can see the majority of it is for cooling spaces and mobile air conditioning, and refrigeration, household refrigerators. So this based on that graph of the cooling demand for India. So here is a projection of how HFC emissions are going to occur over the years until 2050, right? And as you can see, RAC, which is residential air conditioning, and MAC, which is mobile air conditioning, and large refrigerators, small refrigerators. Those are the main sectors which are going to see a very steep increase. And the black dotted line there indicates what Indian allowance, what we have signed as per the Kigali Amendment, right? So we start with 2028 as a baseline year. We start to make some amendments to start phasing down the HFC emissions. So this is the vision for us. So like any other emission strategy, right? To control the emissions, first we need to know what is the emission that is occurring. So at Empri, we are trying to quantify the HFC emissions in Karnataka, district-wise, based on secondary activity data under the following sectors, which are, of course, again, the main sectors where HFCs are being used. So mainly mobile air conditioning, commercial and residential cooling, industrial cooling, cold chain and chillers, and foam and aerosol manufacturing. So this data will be used to further, make a projection based on scenarios about business as usual and sticking to Kigali Amendment, or even our Panchamrit scheme wherein CO2 emissions need to be reduced. There is a target. So based on that, projections will be undertaken. So far we have carried out the HFC emission for mobile air conditioning, that is the transportation sector. So the air conditioning is mainly used in low duty and high duty vehicles. Low duty is like cars, taxis, jeeps, etc., and high duty being AC buses and tempo travelers, etc. So at the charge rate is 0.5 kg per year. Every year, so much of, and 5 kg in case of buses. So that is the amount of coolant that you have in your air conditions in the transportation vehicles. And annual leakage of about 10% occurs through just, regular operation of ACs. That means a bus which is loaded with 5 kg of coolant emits about 500 grams of HFCs per year. And of course, during maintenance or car services, etc., if it goes below a point, it is refilled, and there is scope for more emissions like that, right? So the HFCs that are prevalently used are 134A. It is a commercial name given for C2 HFC. And operation of air conditioning itself uses 15% of the total fuel. So if I'm running 1 liter of petrol, right, 15% of it is used up for cooling purpose itself. And here is a chart of HFC emission in terms of CO2 equivalents in Karnataka. And like any other graphs, it is also seeing a steady increase in the emission, mainly because of increased usage of vehicles. So in 2016, the emission was around 250,000 tons of CO2 equivalents, while in 2020 we have crossed 350,000 ton emission of CO2. And so here, that is the coolant that is used. There's a picture, right? So whenever you go for car servicing, if the amount is reduced or something, this particular coolant is used to refill, and thereby, more emissions occur from there. So what is the solution, right, for HFC emission? I mean, I cannot ask anybody to stop using fridges or mobile air conditioning, but definitely there are several options that are available for replacing HFCs. So one of the more engrossed idea is skipping HFC-based cooling altogether. India is now in a zone of transition where we are more and more depending on air conditioning. So if you see any sales figures of air conditioning systems, right? So it is rapidly increasing for the past 2 to 3 years. So now that we are entering this phase of increased dependence on air conditioning, companies could be pushed to directly switch from HFC as a coolant to other alternatives available, right? Green cooling, which are environmental friendly air conditioning and refrigeration with minimum impacts on the environment. And those refrigerants are propane, isobutane, carbon dioxide in itself, like liquefied. When you put it under high pressure, carbon dioxide is in the liquid form, and that acts as an excellent coolant. And few hydrocarbons, ammonia, water, and compressed air. So these are some alternative options. So ammonia, till some extent, is used in complement to the HFC already, some of the coolants. So we can see like a gradual shift in trend. So more push from the policies has to come, phase out HFCs and use more of these green cooling compounds that have been established to bring in the same cooling effect. And of course, there is improved architecture, that is increase the insulation and give more preference to passive cooling, as we've done in our own campus. So definitely more focus on architectural improvement to eliminate the cooling needs altogether is a much welcomed option. This will also eliminate the dependency on cooling itself, even including the fan. Fan is also running, and even for the fan to run, it requires some amount of electricity that is again coming from coal burning, right? So all of this could be avoided through architectural improvement. And another interesting strategy is district cooling. District cooling is where you have a centralized system for providing the cooling, or let's say in a very cold places like Himalayan belt or something, heating, wherein through pipes, you pass the coolants to the buildings itself. So through this, what happens, you are centralizing your system of passing the cooling agent, right? So if you do like this, the leakages at every small places can be avoided. And of course, investments will take care of leakage at this bigger, charge unit itself. So I'm sure you're wondering whether this is usable for Bangalore, where will you centralize this or something. But I think this is very much, this is a huge potential for housing societies. You have 1,000 home flat or something. So they can have, instead of promoting individual household to have a AC or something, so those people can have like a mobile cooling house itself, wherein they circulate. I'm sure you're all familiar with the idea of LPG through pipeline connection, right? In Bangalore itself, some of the areas have already started having this LPG connection through pipelines, where you don't need to refill the cylinders anymore, but it will be provided you like water through pipes. So the coolant can also be distributed through this. And of course, this is an idea more relevant for a homogeneous population. So, but yeah, definitely this could be something that could be thought about for cities like Bangalore also, right? So, in snapshot, what you need to take home about hydrocarbons is here. So they are mainly coming from cooling, and they have a 15 years of atmospheric lifetime, and they have 1,500 to 3,000 times higher global warming potential compared to carbon dioxide. And unlike other climate pollutants, there is hope for HFC emission reduction. So it just requires a strong push from the industries and the policy end to adapt more climate-friendly policies. So with that, I would like to end my talk. Thank you very much. Any questions? Yes, please. HFC, sorry? At the source level. By source, you mean? No, that is definitely there. Like I said, HFC emission is mainly from leakaging, right? So like more and more, like as you go, for instance, if you take mobile air conditionings in the cars and all, so with every model, they're trying to upgrade the system to avoid leakages, but this is not intentionally happening, the HFC emission. So technological innovation is definitely happening. And also for the air conditioning, regular servicing, that can also avoid HFC emission, and the new models that are coming up, they're also having some measures. And in terms of industrial cooling, since it is leakage, they are only trying to focus on plugging those leakages, right? So by plugging them, first, they will spend less on refilling it, right? Even it will cost some amount to refill this HFCs. So technology is there. But the focus is mainly on, inventing or depending on coolants that are not climate pollutants anymore. Like I mentioned, ammonia or other hydrocarbons, propane, isopropyl, etc. Thank you. So if there are no more questions, I take that you all have a good idea about hydrofluorocarbons and their emissions, and about not turning on AC in your cars anymore. Thank you very much for joining us.
Thank you, Dr. Tejaswini, for giving a brief insight on hydrofluorocarbons and climate change. Now I request our Director General, Dr. Jagmohan Sharma, to share his thoughts. Okay, thank you all. On behalf of Empri, I would like to thank the guest speaker, Professor Gufran Ullah Beg and Dr. Tejaswini Ami, for your insightful and thought-provoking presentation. I would like to extend my thanks to Dr. Jagmohan Sharma, Director General Empri, for providing immense support to make the webinar successful. Thank you all for participating in the webinar. I hope your knowledge has been expanded by this talk, and thank you all.